Hi, I'm Carson McCormick. I'm enrolled in Physics 221, and today for this lab report I'm going to be discussing frictional forces in relation to material of a block sliding down an inclined plane. Friction is a force we encounter in our everyday lives, helping us to walk, drive, and do other normal tasks. Without friction, walking would be an impossible task as there would be no resistive force to counteract our motion in the other direction. It can be observed that most shoes are made out of some type of rubber sole, and the goal of this experiment is to determine, using a simple setup, how much the choice of material can affect the frictional properties of an object. My setup for this experiment includes a meter-long ramp set at 37 degrees from the horizontal, and a small block of wood which weighs about 40 grams. For different trials, I attached different material of negligible mass to the bottom surface of the block, simulating a change in material. Two sample trials follow, one with a block with no foam attached to the bottom and one with a small piece of foam attached. In order to analyze the results of this experiment, I placed the video I recorded of the block sliding down the ramp into Logger Pro. This allows me to plot a coordinate plane relative to the axis in the video, set a scale, and place points to create a graph of the block's motion. It can be seen here that as the video progresses forward, the points on the x-axis increasingly come farther apart. This means that the block is accelerating while it is traveling down the ramp due to gravity. After repeating the same process in Logger Pro for both trials, I came up with these two graphs shown above. Before we get into the analysis of these graphs, a couple definitions need to be cleared up. First off is the definition of static friction, which is a resistive force which occurs upon contact of two objects and works to keep them in place. An example of this is a car driving on a road where the tire stays in contact and does not slip along the surface of the road. The next definition is kinetic friction, which is the force between two moving objects or one moving and one stationary object, such as a block sliding down a ramp as shown in our experiment. This is the type of friction we will be calculating later on in this video. And a final definition is Newton's second law of force equals mass times acceleration, which we will use for the calculation of the frictional forces later in the video. Going back to the graphs and videos from earlier, we can see some obvious differences between the two blocks. In the video, we notice that the block without foam slides much faster than the block with foam, meaning there must be a much weaker force resisting its motion. We can prove this with the graph by noting that the block without foam reached 2.5 meters per second at the 0.6 second mark, whereas the foam block was only traveling about 0.3 meters per second at this point. It is also important to note the differences between the curves of the two displacement graphs, and those are the lines shown with round dots on each graph. With the scale of axes Logger Pro has given us, it can be hard to visualize, but the curve on the bottom is much sharper than the one on the top, signifying they cover the same distance, however the block with less friction did so with a much more rapid acceleration. When we add a line of best fit to the graphs, we can see the difference in the actual values of the acceleration, which for high friction versus low friction were 0.41 meters per second squared and 4.47 meters per second squared respectively. This shows not only the calculus-based relationship between displacement, velocity, and acceleration, but also how large of a difference in motion the seemingly small piece of foam creates between the two blocks without changing the mass at all. One conclusion that may be drawn from this is that a porous surface such as that on the foam creates a higher coefficient of friction and allows the surface of the block to grip the ramp more easily. In order to calculate the actual values for the forces of friction in newtons, I use the two equations above. F equals ma, and force of friction is the coefficient of static friction times the normal force. To begin solving, I created a force table for all of the known and unknown forces at work in this situation. This includes the forces of friction, the normal force, and the force of gravity. Both equations for net force are shown, with the equation for the y-axis being equal to 0 since we do not have any acceleration in that direction due to our choice of axis. The next step was to set the net force for the x-axis equal to the mass times acceleration, since this value will be equal to the total net force on the block and will allow me to solve for the value of friction alone, as the force due to gravity is counted as a known quantity found by using trigonometry. This setup equation is shown here. Next, I solved for the value of gravitational force and plugged in the values for mass and acceleration, varying with the acceleration value for each block. This left me with my only unknown as the force of friction, which is easily solved for using simple algebra. Shown is the equation for the block with foam attached. After completing calculations for both blocks, I found the force of friction for the block with foam to be equal to negative 2.97 newtons, and the force for the block without foam equal to negative 1.34 newtons. These calculations make physical sense and illustrate how a small change in force for an object with a smaller mass can mean a large change in that object's kinematic motion. It's also important to note the uncertainty in this experiment, which is most likely due to human error using the LoggerPro software. In order to correct this error, the experiment would have to be repeated multiple times in order to create a proper Gaussian distribution and take the average based on this. To conclude this experiment, it's now possible to state that material has a large effect on the frictional forces of an object, especially one with a smaller mass, and that more porous material, such as foam, can dramatically slow an object's acceleration down, demonstrated by the results of this experiment, and that this concept can easily be applied to many real-world situations in everyday life as well as in a field such as engineering.